Hello, welcome back. Today we're going through parts F to M on question 1 of 2011's C3L6 paper. So this is the paper that Year 12 students do at the end of their first year of A-level studies. But the content in the exam tends to go past both Year 12 and sometimes Year 13 content. So really, it's a lot like a chemistry Olympiad. It is the precursor to the chemistry Olympiad. So today we're going through. Last time we did a lot on enthalpy changes, but today we're going through a lot of structure determination, and a lot of it is just applying what you know. So let's start. So we get told this lovely summary of information. So this is all you're expected to know. Okay, so in order to investigate the mechanism for the conversion of reaction B to A, samples of the compounds have been prepared with some normal hydrogen replaced by deuterium. When drawing structures for the rest of the equation of the question, use skeletal formulae, and so do not explicitly draw in any hydrogen atoms. So they've given a few examples of how you show the D for a deuterium atom, but you do not draw the H's for hydrogen atoms. And so you have to try and remember also the geometry, the 3D shape that a carbon atom, when it's sp3 hybridized, it's tetrahedral, is essentially. So you've got to try and include the 3D structure with the wedges, the dashes, and the straight lines. So they give you examples. So they say down. Hang on a second. Let me just. Right, here we go. We're in business. So this is incorrectly drawn because we have. It's not tetrahedral. So you have to really look at the shape. Here, it's that is a funky pyramid. Here, this is good because you have this two is straight, and then one coming towards us here, and one going away from us here. And this just tells you information. If you didn't know what in the same environment meant, then it's given you an example. So you can still do the question because later on it mentions the same environment. I mean, to be honest, it's something you only really discuss in year 13. And you also get told that these are correctly drawn, and they tell you more things about this is what a different environment is, and this is what the same environment is. And so they also introduced this idea of an enantiomer. Now, an enantiomer is where there is a chiral center, which gives rise to two non-superimposable mirror images. So if you think about your hand, your right hand is a mirror image of your left hand, but if you put one on top of the other, they don't align. Your thumbs are the wrong way around, if you like. So that's the same with a molecule, where you have something where there's a carbon atom and there's 4 different substituents coming off of it. Because you have to take into account the fact that it's tetrahedral, there'll be 2 different versions of that. So they're called enantiomers. Oops. And so we'll need that in a second. Right, we jumped quite quickly in. Replacing one of the hydrogens in compound A or B with a deuterium gives compounds of formula C3H5D. So this is essentially just deuteration. But you don't have to think about any mechanistic way to make it. You just have to draw them. So here, we're just drawing. So we determined from the previous question that this is A. And if you didn't get that, you're sort of stuck. So that's the problem with some of these questions. You have to get the first ones to be able to do the rest. But this is A. And so if you replace A with a deuterium, there's actually 4 ways to do it. So the first way is, how's the best way to do it? I'll just draw them. This is number 1. And then you can also think, if you've got to be careful with this double bond, because that's the second way. But then if you also, then down here, you can have a deuterium coming out here, which is different to the structure where a deuterium comes out here. So there are 4 ways. 1, 2, 3, 4. And you'd get 4 marks for that. If you drew a structure and accidentally you drew the same one twice, then you'd get -1 mark from whatever mark you got. So let's say so that would be 4 marks. And then here we're doing it with B, and we discussed that B is just cyclopropane. And so cyclopropane, if you think about what happens, if you add a D here, it's completely the same as if you add a D here and if you add a D here. So in reality, there's only one structure, which is this. So there's one structure, because they're all equivalent. And so if you do draw 2, you immediately get 0 marks. Right, this is a blank screen for what's happening next. Right, here's when a lot of the drawing comes in. You've just got to be confident. So now if 2 of the hydrogens are replaced with deuterium, there are 7 structures that emerge. So this is just adding another deuterium to what we had before. These isomers are labeled A1, A2, blah, blah, blah. And in isomer A1, the 2 deuterium atoms are in exactly the same environment. And we got told what the same environment meant in the previous information. For all the other isomers, the 2 deuteriums are in different environments. So I propose that we actually just draw out different ways you can do it. I've done this on an A4 sheet of paper, which is a lot easier, but we could do it online here. Now, if we're thinking about the ways you can add you can have 2 deuteriums on A. So let's just have, this is A, just as a reminder. You could have, with the A is that you could also draw A as that. So if we have A up here as that, we have, well, I'm going to call this one A1, and then, well, this does happen to be A1, but I'll go through that in a second. Then if we have another way to do it, this is another. Then we have another way is going 1 over each end. I've messed that up. It should be 2 singles. Feel free to keep going. I'm going to revisit this in a second because we've already got our answer here of A, and I'll quickly explain why this is A and why the others can't be A. So A1, if you look here, if you have the D's both here, what actually happens with a single bond around this carbon atom, there's rotation. It can freely rotate. And so these 2 deuteriums are in exactly the same environment because they're bonded. They're both bonded to the same carbon, which is all bonded to a single straight bit, and this rotates. So it's exact. They are in the chemically equivalent environments. But if you looked instead at something like, if you had them both here, there's no rotation here. So you see this one lines up here. This has some steric interaction, which means that this is this D down here is different to this D up here. And so if you look through all the structures, you find that the only one that can be A1 is if it's drawn like this, which is exactly the same as drawing it if you drew it the other way around, like this. And this is actually what the mark scheme says. So this is A1. Right. Isomers A1 to A7 react with deuterium gas. So this is deuteration. Presence of a metal catalyst, that's basically irrelevant, adding 2 deuteriums to the molecule. So now we have 4 deuteriums. During this process, some of the isomers form a single compound, so only some. Other isomers produce a pair of compounds. This is what we discussed earlier, enantiomers, non-superimposable mirror images like your hands. So they have a carbon atom with 4 different substituents, like I discussed. If you have, let's say, A, B, C, and D, if you rearrange these two, you get a different molecule. And so that's the idea of it being a mirror image. If you reflected it down this line, you'd have, right, let me just draw this properly. You would have this. But now this is chemically different to before, because if you try and rearrange it, you get that these two are now switched. It's wedged where it was dashed, and it's dashed where it was wedged. And so those are enantiomers, they're called. Now, the next question. On deuteration, A1 gives a pair of enantiomers, X1 and X2. So let's just remind ourselves, A1 was this. Bam. Now, if we have ways, we need a way to add 2. So we're adding D2. And we're drawing it to give, there has to be a carbon atom where there are 4 different substituents. And so the way we do this is it would have to be added on this carbon and this carbon over the double bond. So we keep this bit the same as usual, but we're adding an extra 2 carbon atoms, an extra 2 deuterium atoms. So what happens is actually that, so if you add a D here, this D is single bonded, so it doesn't matter if you put it as a wedge or a dash, but this is just a straight line. And then here, this does matter, because 1 is a D like that. So this is, let's say, X1. You don't need to say which is which. You can't tell which is which. And the other way you could draw it is with a dash, up to D, and then D. So those are the 2 structures. Make sure that they're really looking for the dash versus the wedge. And so the idea is that if you had a mirror between these 2, they'd be mirror images. So that's X1 and X2 done. What it means, you might be asking, why would they even bother saying this? If you go into high-level organic chemistry, you find out ways to name the different enantiomers. So you can look at things like R and S and different letters and ways to show to show which way it is, whether it is a dashed or a wedge. But that's quite advanced. Okay, so compounds A2 and A3 now. These also form the same compounds on deuteration, but we have to find those two. Okay, so this is where I think it's the easiest way to do it, is just to draw out all of the structures. But obviously I can't do this in the small space that you have there. So I'm going to shortly explain that if I show you these two. So this was A, remember? And if you add D to either end, you get one of the A number products. So one possibility is if we have a D on either end like this. This is quite badly drawn, but this, if you deuterate it, you can only add across the double bond, because we're not replacing hydrogens, we're just adding. So we add a D here, but then if you look, this could be a wedge, or it could be, instead of a wedge, it could be a dash. So this is one of the A's that we need. This is A2. Let's call it. You might say A3. I'm saying A2. And the other one that you would use is quite similar to A. So this is A2, and A3 is this. So this bit in the middle, this is A, if you remember. But A2, actually didn't mean to do that. A2 is when, if you deuterate this, so deuteration is the same. You might have come across hydration or hydrogenation. This is just hydrogenation, but you're adding hydrogen 2. And so it would go across the double bond as before. So this could be a wedge. And then bam, bam. Or this bit could be a dash. And so that gives you the two enantiomers as before. So let me just quickly draw. A2 is this. A3 is that. So that's the way the mark scheme gives it. But this is yeah, you could draw it in any orientation as long as you have the connectivity right. That's what they say. Right, let's keep going. Now, A4 and A5. So we've dealt with 3 of the 7 so far, but we have 4, 5, 6, and 7 still to do. So they give the same single compound, and this is a single compound, so we don't need to worry about stereoisomers. A stereoisomer, so an enantiomer is a stereoisomer. We don't need to worry about those. So if we think now in terms of, so we're on J, we can draw the structure of Y. I honestly think, I'm repeating this, but if you draw all the structures out, you find that the only possibility is that the D's are arranged like this. And so this is Y. And so the way to get A4 and A5 is essentially to remove 2 deuteriums in some way and see what happens. So if we removed this one, and we removed, let's say, this one, then what you get left with is A4. And so you'd be left with a D here, and a double bond, and a D. So this is A4. And what you might recognize is that whenever you have a double bond, since there's no rotation, you don't have to think about, this one and this one. You can just see straight from A4 that it's going to be, so A5 will be just inverted, basically. So the D is changing position from here to down here. So that's A4, that's A5, and that's Y. And so that's another section. That's another 4. Oh, it's another, how many marks? 3. It's another 3 marks. 1 for each structure. Now, we're on K now. Okay, A6. So we've just got 6 and 7 left. A6 forms the single compound Z on deuteration. So we've got 1 to 1. We had previously that 2 structures form the same one, which was Y. But now we have one is going to 1. So there's no stereoisomers still. And we need to think about, there's not going to be that possibility of the inversion around the double bond like there was before. Like, that you're not going to be able to do that, because that would mean 2 compounds get the same thing. So if you look through the possibilities, and I encourage you to do so, you find that the only possibility is that this is D. Sorry, what am I on about? Not D. This is A6. Okay, I'll redraw that because that wasn't very clear. This is also, I've just drawn it backwards. This is A6. Because if you add a hydrogen, if you add a deuterium to this atom, you get one here, and then you would also get one here, and this rotates. And so it doesn't matter how you draw it, because it will give you the same molecule. And there's not that double bond inversion, which means there's only one structure. So it has to be A6. But so if we know A6 now, we just need to add 2 deuteriums to it. So I basically just did it. You get DD, D, D. Now you could also draw this D coming down here. You cannot draw both at the same time, but if you drew it up there or down here, it's equivalent. So this is Z, and this is A6. If you actually look, it's symmetrical, which could be another clue, because it's only one structure is forming. And so if you have a symmetrical molecule, the mirror image will be the same. Now, compound A7 forms a pair of enantiomers on deuteration, but they are different from X1 and X2. Now, if we just remind ourselves of X1 and X2, because it could help, they were this. With a D here, which was either a wedge or a dash. Now, it can't be that. So if you had drawn through all of the different possibilities for the A structures 1 to 7, then you wouldn't need to do any work, because you'd automatically have that this is the remaining structure. So this is A7. So you wouldn't need to think about any of the enantiomers if you had just drawn all of them. So that's that question. Now, this is when we get told more about symmetry, rotational symmetry, and planes of symmetry. It's fairly straightforward and intuitive, but let's just go through it. It can be useful to classify molecules by the type of symmetry they contain. Molecules may or may not contain a plane of symmetry, and they may or may not contain a rotational symmetry. Straightforward. A person has a plane of symmetry, but no rotational symmetry. That makes sense. two identical twins can be arranged in different ways that exhibit different symmetries, as shown below. And it gives you examples. So this one has no symmetry whatsoever. This one has a plane of symmetry, but if you rotate it, you can't get back to itself. Whereas this one has a plane of symmetry. This one has no plane of symmetry because down that line, one's facing one way, the other's facing the other. But if you did rotate them, then they would have rotational symmetry. And here, down here, number 4 in Roman numerals, this has both rotational symmetry and plane of symmetry. And so what they're going to ask us to do is, we've done a lot of stuff with A. We've got B to deal with now. Compound B, which, remember, B is just cyclopropane. And now, if we are replacing 2 of the hydrogens with deuterium, we get isomers. And now, these are all cyclic. We've got to remember, we're not breaking open. We're just replacing. We're not adding, we're replacing. So if we were adding, we'd have, if you remember in the previous question, we added bromine to it and it looked like this because it opened up. But we're not going to open up because we're just talking about adding. We're talking about replacing hydrogens, not adding extra to the hydrogens. Now, structures with 2 Ds, and one of these. So, if you get thinking, there is a possibility of, well, you don't need to draw this sort of the wedges. You can just draw that the possibilities are, if you have this, a D there and a D there. If you have this, a D up there and a D down there. If you have this, both D's on one side. And you could also have this, but revert this one. Don't know why it's not working. You could also have this one reversed. Now, strictly speaking, you should have. I'm certain you should have the wedges, but the mark scheme's not strict on that. They just want to see symmetry. Now, we've got to just we've got to arrange those structures according to symmetries. And what you actually find, it's a bit of a trick question. None of them have both. None of them, so they all have a kind of symmetry. And then if you arrange it, it was, this one was here. You also have 2 down here. Well, I'm gonna draw a bit more clear. Up and down, and then down, then up. And then finally, you have it here. Now, if you think about the wedges and the dashes for a second. If I did draw in over here, if I drew wedges, you get 2 different structures, but they're the same because you can rotate one onto the other. So these are superimposable mirror images, you'd say. So they're not enantiomers. Now that's all for the question that we have now. We've actually just completed the question. So I hope to see you soon for some interesting stuff on question 2 from this paper. And if it's been useful, you know what to do, all the due diligence of subscribing So I'll see you soon.